we just looked at underdamped oscillations and saw that there was a function that describes that, and then a graph that makes sense based on what underdamped oscillations look like in reality. But now with this example, we're going to look at how you get to critical damping. And it turns out this informational example is what's going to get us there, because it says what happens if beta is equal to omega naught. And beta was equal to b over 2m, where b was the actual damping coefficient. So conceptually, beta corresponds to the amount of damping the system has in relation to the whole system. That's why you have to kind of relate to the amount of mass that was there. But it's saying, well, what happens when that's equal to what one could regard as the natural angular frequency of oscillation of the system in the absence of damping? That's really what omega naught stands for. And it turns out that changes the solution. So the complicated mathematical formula we had before is now replaced by another maybe still complicated mathematical formula, but a different one. And this is the x as a function of time that corresponds to critically damped motion. And it really only happens mathematically at this very specific place in parameter space where beta is equal to omega naught. In that sense, from a physical measuring perspective, one could ask, does this ever really happen, right? Because we know that all values that we can measure about the reality we live in always have uncertainty, and yet I just said this only happens when these are exactly equal. So my answer would be no. This really is represents that mathematical boundary between underdamped and overdamped. But let's see what this is all about. This example says, what does a plot of a critically damped oscillation look like with initial speed equal to 0? So we can look at that and then contrast that to what we saw before for underdamped oscillations. With underdamped oscillations, you definitely still saw the up, down, back and forth movement that we associate with simple harmonic motion. This, even though this is named a critically damped oscillation, really doesn't even look like an oscillation at all, because it just goes down and then stays there. And the characteristic that it has is this represents the fastest route back to equilibrium in parameter space. So sometimes it's described as the ideal place to be if you're designing a suspension system for a car. I'm not always convinced. I've seen textbooks and I've seen teachers, especially in math, say that. But whether that's really true, I think is a little bit debatable, because, as I said earlier, considering measurement errors, taking those into account, if you're right on this spot, all it would take is maybe a little bit of wear and tear in the system, and now you're in underdamped, which is not desirable. So it might actually be more desirable for a suspension system to start out overdamped, basically give yourself a little bit more damping, and then over time, as the shocks wear out, at some point you'll cross that threshold from overdamped to underdamped, and that's the point to replace the shocks.